Okay, thank you very much for the invitation. In a nutshell, what I'm going to do is to take the techniques that Lior was describing in his first talk and apply them to completely different problems in the natural sciences. Why would you want to do that? You could have many reasons. Some people are interested in companies. Some people don't like the competition with Microsoft, Yandex, IBM, Google, Facebook, etc. But for me, the real reasons is the beauty of the problems. I hope I will convince you that the problems are really beautiful. So natural sciences, scientific discoveries, there is obviously three drivers that you know very well: the data, computing, and machine learning, or for me, it's going to be deep learning. And to see this process, it helps to a little bit look at the history. And if you go back to the sort of beginning of science, right after the Renaissance, Galileo, you can see that he built this instrument, this telescope. He had no iPhone. He couldn't order it from Amazon, so he built it himself. And this had a magnification factor of 20x, right? And it was a very primitive telescope, but of course was incredible at the time to look at the skies. There was no pollution, magnification of 20, and you can see that there is no real data collection, right? Of course, he could write down the coordinates of some planets on a piece of paper, but that was the data collection at most. Everything is done by his eye and by his brain. No computers, no data. How do things look today? Pretty much the same thing. It's still a telescope. You cannot order it on Amazon. It is in space. It's called the Hubble telescope in this case. The difference is you cannot put your eye here, right? You need, of course, computer. You need databases. This thing is producing terabytes of data, watching the sky. And of course, now the problem of learning, of understanding the data becomes much more complicated and requires machine learning. Now, with the Hubble and other instruments, you can see now galaxies that are 13 billion light years away from Earth. The Big Bang occurred about 13.7 billion years away. So galaxies that were produced relatively short time after the Big Bang. You can study the Big Bang from the other side. And this is the Large Hadron Collider at CERN in Switzerland, where you accelerate protons to the speed, close to the speed of light, and you smash them together. It produces a shower of particles, derived particles, that hits 100 millions of detectors around the collision points. And these collisions occurs on nanosecond scale. So this machine produces 1 petabyte of data per second. A petabyte is just a gigantic amount of data. In fact, you cannot store it. Most of it you have to throw away, and it's a big problem. But just to give you an idea of how things have changed, you cannot buy this on Amazon. No, I'm sorry. This you can buy on Amazon. It's a DNA sequencer produced by Illumina. And today, in one afternoon, you can sequence a full human genome on this machine for less than $1,000. When the first human genome was sequenced, it cost $1 billion, and it took 11 years to get there. But today, this machine routinely produces data that looks like this, that of course human cannot understand. This is the full genome of the AIDS virus. And yours is the same thing, but it's hundreds of thousands of pages looking like this, right? And of course, there's many other sensors. Everything is producing data, and you know all this. We have much better computers than Galileo, GPUs. I'm not going to say anything. Machine learning, how did it start? Well, you can argue the beginning of machine learning is here, right? It's linear regression. Gauss is one of the first mathematicians who worked on this. But everything we do today is pretty much in this picture, right? You're trying to find a model. You're trying to compress the data. You study the variation around this. You can compare model. You know, is there a sinusoidal trend in this data or not? All the questions about machine learning, you pretty much can see them in this simple picture. Except today you want to do linear or nonlinear regression in very high dimensional space with very large amounts of data. So if you have something like this, you need much more flexible functions than linear functions to try to fit data that looks like this. And of course, we have deep learning, neural networks. You can use Gaussian processes and all kinds of things. But in a nutshell, this is pretty much what is going on. As you know, on the engineering side, whether you take speech recognition, image recognition, natural language processing, all those things, in the last few years, deep learning, big neural networks essentially have had a profound impact. This is the ImageNet thing. For many years, the arrow curve was sort of flat. This has been said, and it was the same thing for speech recognition. And then the last few years, you see this rapid drop. Currently, I think the best, I don't know if this is the latest, but this is the latest I know of, is about 4.9 or so in error rate, which is believed to be superhuman, better than what humans can do. So what we're going to do, and you know everything about deep learning, is to apply this to the natural science. Now, I disagree with those who think that there is no theory behind deep learning or behind neural networks. There is actually quite a bit of theory, except not everybody knows about it. It's not complete. There is pockets of theory here and there, but we know a lot. We know, for instance, how many functions can be implemented by a threshold unit. We understand compressive autoencoders fairly well, both in the linear and nonlinear case. We understand universal approximation properties, etc. So there's a lot of things that actually can be understood about neural networks. And we have a lot of tools or understanding for the design of neural networks, certainly for the design of the output layer, for the design of autoencoders, if that's what you're using. And definitely, we know about how to design recurrent networks, and that will be important in the examples. Some of the examples I'll show you to you because I will use recurrent neural networks. Another thing that has not been pointed out that I want to mention is the importance of group theory in machine learning. I think this is underestimated, but group theory actually is starting to show up in many places in machine learning. Of course, is what you're trying to learn or to predict is a permutation of the objects. You have a lot of machine learning there. But other places is if you want to do recognition in some invariance way, whether it's translation, rotation, etc., you have to adapt the architecture to this translation invariance. The best example known is weight sharing for translation invariance, but it's a much more general question, right? And there is quite a bit of theory from grouply theory, actually, that can be applied to deep learning to build architecture that have invariance with respect to particular groups of operations. And this also will pop up in a simple way in one of the examples that I will describe to you. So let me just say the design of architectures, of recurrent architectures. When you have inputs that are fixed vectors of fixed size, you can use feedforward architecture with or without weight sharing, etc. The problem is when you have inputs, objects, when you're dealing with data that is of a different format, where the vectors or whatever objects you're dealing with vary in size. For instance, sequences, DNA sequences, protein sequences, they're variable length, and they are not vectors when you get them. And you could have inputs that are trees. You can have graphs in chemistry. I'll show you examples where we have graphs as the input. Then you cannot use a simple feedforward architecture. It's absolutely essential that you use a recurrent neural networks. And one general technique for building this is that if you have a directed acyclic graph, a DAG, typically the ones that come from Bayesian networks, what you do is simply parameterize the relationship. You have variables on the nodes, and the relationship between two neighbors like this is parameterized by a neural network. So you have a neural network that computes this node as a function. You have two neural networks, if you want, that computes this variable as a function of these two variables, etc. And if your directed acyclic graph has some regular structure, it's a lattice or it's a tree, etc., you can, of course, do weight sharing so that this neural network and this neural network, for instance, are forced to have the same weights, right? And you will see that in my presentation. And as long as the graph is acyclic, you get, when you unfold, this is just a large, very deep neural network. You can do backpropagation through it, etc. So, for example, if you take an HMM, standard graphical model representation of an HMM is like this, where you have the transition between the hidden states, the productions, the letters that are being produced by the system. And again, you want to transform this into a deep neural network. You just have to put a neural network on these edges. And if you do weight sharing, you have a single neural network that is controlling the transitions, now in a deterministic way. And then you have a neural network that takes care of the production of the letters from the whatever vector describing the hidden state here. So, and again, you can do weight sharing here, so you get this whole HMM can give rise to a system that has two recurrent neural networks, one that is taking care of the production and one that is taking care of the transitions. And I will use this trick in at least one of my examples. So this is how it looks like. You have these neural networks, and this one, you can tie the weights of these two neural networks as well as these three neural networks here. OK, so applications, finally. Where am I? I'll show you different applications in physics, in chemistry, and biology, just to give you an example of the breadth you can achieve with just the same set of techniques. But the same thing is in engineering, right? Deep learning is used for images, speech, natural language. I'm doing the same thing in the natural sciences. And what I'm describing here is just the tip of the iceberg. I mean, there are tons of problems in the natural sciences. I just don't have the resources, but there is plenty of things one can do. So I'm going to show you problems in physics, especially I'm just going to take the first one, high-energy physics, identification of exotic particles. This is data from the CERN collider. Chemistry, prediction of molecular properties and chemical reactions. So we're talking here about small molecules in the 10 of angstrom range. And then one example from biology where I will use, well, in these two cases, I will use recurrent networks to predict protein structure and structural features. So high-energy physics, I told you there is this large collider. This is a typical human being. It has a lot of components. I have no time to go into the details, but it produces very large amount of data. And what you're dealing with are really the fundamental laws of physics. This is the table, if you want, of the particles in the standard model of physics, which is the main model for physics. It has been incredibly successful at explaining most of the things we see. However, we know it is wrong because, for instance, it doesn't explain dark matter and dark energy. And so we know that this model has to be changed, and the collider plays an essential role in trying to find what are the new laws of physics that could provide a better explanation, that could explain dark matter and dark energy. It's also a way of going back to the Big Bang, because what you're doing is a mini Big Bang inside the accelerator, and there are particles that probably existed around the Big Bang, the time of the Big Bang, for a very short period of time, and then decayed. And these particles, you cannot observe them in the universe today. So in the collider, you are trying to recreate the Big Bang and to see what are these so-called exotic particles that may have existed for very short periods of time after the Big Bang, and that could help to also to resolve this problem of the standard model. So there is a lot of understanding in quantum mechanics related to the standard model and how to build these so-called Feynman diagrams, where you have you build these diagrams of how the particles interact. And if you want, you can use this to look at the experiments that you're doing in a collider, look at what is a possible background, what is a possible signal being an event that produces these exotic particles. Everything is probabilistic, it's not deterministic, so even if an exotic particle is produced in a collision, it happens very rarely, just a few collisions out of many billions. And you can use this knowledge, as you will see, to build data, simulated data or true data. So we have been now applying these techniques to various problems. So detection of exotic particles, for instance, the Higgs boson is a famous one, but also supersymmetric particles. We have been applying it to how the Higgs boson decay. Physicists have different theories about the decay of the Higgs boson. And more recently, we are been tackling other problems, such as what is called the Jet substructure and jet tagging problems. These are problems that occur upstream of these problems, as I'll show you in a moment. So in the interest of time, I'm just going to show you the first one, the problems of detecting Higgs boson. But in all these three problems of particle detection, you have inputs that are of fixed size, vectors of fixed size, and the data we're working with and the data the physicists are working with is at the end of the pipeline. I'm not working at the level of the petabyte per second, where you have to filter the data very rapidly and throw away most of it. There is interesting machine learning to be done there. It's called the trigger. But here we are downstream of the trigger. After there is a detector called the calorimeter, there is the tracker. Once you pass the calorimeter and the tracker, you get vectors of fixed size, which are essentially the momenta of the particle around the collision point. And from there, you want to decide whether Higgs boson was produced or not, right? So it's a classification problem. You have very well-defined data. These are vectors, real vectors of length, 30, 40, something like this, depending on the problem. So we can generate data. The physics is well understood. So you have simulator, if you want, where you can generate data, or you can use data from CERN if you have access to their data. So we have millions of examples. It's a classification problems. And physicists, of course, have been dealing with this problem for a while. And they have been using handcraft features. So right there, you know that there is an opportunity for deep learning. These handcraft features are just complex mathematical formulas that are derived from these vectors, from these momenta of particles. And so using deep learning, you can see that you can essentially get rid of these handcrafted features.
Pierre, just have a quick question here. So in terms of classification, how many classes are there?
The example I'm going to show you, there's going to be only two classes. There's going to be Higgs or no Higgs in this example. But there are other problems where I could show you problems with more classes. So that's how the Feynman diagrams look like. This is a collision that produces Higgs bosons, and then they decay into W bosons and in bottom quarks. And this is the model for the background process, right, which produces slightly different signals. The data sets we have in this case is of the order of 10 million examples. This is work done with Daniel Whiteson. This is a physicist at UCI who is also part of the Atlas Consortium at CERN. This is Peter Sadowski of students in my group. So we have 28 features, vector of like 28, if you want to use the full vector. 21 low-level features, which are essential momenta of the particles, and then 7 high-level features derived by physicists. And you can see when you plot the histograms between the events and the background that you see there are tiny differences, which is, of course, what you're going to use. Yes?
How did you get the balanced training set?
We have very good simulators. So these tools here, which I didn't write, of course, are the tools physicists use to produce data. And if you want to go into the details, this is a quick way of producing data. There are slower simulators, which are believed to be more accurate, but there is disagreement between physicists, etc. So we could talk about the data for a while, but this is what I'm using in this example, is data produced using these tools. So this is the slide that nobody wants to talk about, the dirty laundry behind tuning the neural networks. So we use typically neural networks with, in this case, 5, 6 layers. We tried all numbers of layers, typically a few hundred units per layer. There is no weight sharing. Everything is fully connected. We try all the usual tricks. We try dropout, etc. I'm skipping. It's not interesting, but of course that's where a lot of time is spent. And the bottom line is this. So physicists, they draw their ROC curves in the opposite direction for a variety of reasons. But the tools they were using were these artificial features, human-derived features, and shallow learning methods or things like boosted decision trees. So using their tools, this is the kind of AUC we get, using low-level feature only, using high-level features only, or using both. So the best they could achieve was 0.081 AUC. We train lots of neural networks, but this is an example with shallow neural networks, a single hidden layer, and this is a deep neural network. And we get the best result here. And there is not much difference, actually, not much difference between whether we use only low-level or low-level plus high-level features. There's a very tiny difference there. So bottom line, you can improve AUC by about 8%, which is very significant. As you can imagine with this kind of data, it costs hundreds of millions of dollars to just operate the Large Hadron Collider each year. And so this is significant. And we see essentially the same thing on all the particles that we tried, whether it's supersymmetry or Higgs boson decay, etc. Just a small experiment here. There is this idea of compressing neural networks using dark knowledge you may be familiar with, where you train a deep network and then you use either the very top layer or the layer before of the deep neural network as targets to train a shallow networks. This is useful in cases where you have to put your neural network in a cell phone or something like this. You need to compress your neural networks. So in the output units of a deep network, there is a lot of information besides the dominant class. You have a lot of information in the other probabilities. That's what's called the dark knowledge. So doing these experiments, for instance, apply to the Higgs boson case, you can see that the raw neural network, shallow neural network, does 84. Whereas if you train the deep and then use that to train the shallow, we do improve the shallow to 85, but we cannot bring it to 88. So at least in this example, and we have seen this in other cases, this dark knowledge trick for training shallow networks is very useful, but it's definitely not as good as the deep neural network. And of course, it gives a nice paper because you can put dark knowledge and dark matter together, although they have nothing to do with each other. Okay, let me shift. By the way, there is an interesting workshop at CERN for those of you who are interested. Next month, in early November, there's going to be a big data workshop at CERN, and a lot of these things are going to be discussed. And I showed you really the tip of the iceberg. You can apply deep neural network in all parts of the pipeline, in the tracker, at the trigger, etc. And at the trigger, where things are very fast, compression may be very interesting. Anyway, let me shift to a completely different set of problems. In chemistry, you want to predict the properties of small molecules or reactions. In particular, I'm thinking about organic chemistry. So you have a small molecule. It typically looks something like this. You've seen this in high school chemistry, probably. You want to predict the properties of this thing. It can be physical properties, chemical properties, biological properties. Really, the number of properties is almost unlimited, right? You can ask what is the melting temperature of this molecule, what's the boiling point, etc. You can ask, is it soluble in water? Is it soluble in some other liquid? Is it toxic to mice? Is it toxic to E. coli, etc., right? So as long as you get a training set, and that's a big problem in chemistry, I won't talk about that, you can train neural networks or kernel methods. We've done it with kernels to try to address these prediction problems. The nice thing about molecules is that you have many different representations. So this is the graph representation that you're used with. Of course, this is a three-dimensional object, so I could give you the XYZ coordinates of the nuclei in this molecule. You can represent it as strings over a language called SMILES, and I can teach you how to speak SMILES in 5 minutes. You take this molecule, you start with the nitrogen. You can forget all the hydrogens because they're only there to fill the valence rule, so forget the hydrogens. Nitrogen, you go here, Then you can go left or right. So this is a carbon. You don't put the carbons because they are implicit, right? So from the nitrogen, you go to this carbon. You can go left or right. So you open the parentheses. Let's say I go right. I get another carbon and then an oxygen, so CO. I'm at the end of the branch. I close the parentheses. Now I go the other direction. I get a carbon here. Now I branch out, open the parentheses. I have a double bond. You put equal sign. Oxygen is here. I am at the end of the branch. I close. Then I finish. It's an oxygen, right? Of course, you have cycle, benzene. Then you use lowercase c, etc. There's a few more tricks, but really, in one day, you can learn how to speak smiles.
Is that invertible in this case? Or do we have a unique?
It's invertible, yes. And then you have, if you don't like strings, if you want vectors of fixed length, I can give you that. These are called fingerprints in chemistry. And basically, you have a binary sparse vector where you put a 1 if a particular feature is present in the molecule or not. So the question is, what is the basis of features you use? 60 years ago, when people started this, they had handcrafted features, so they were looking for a particular group, a carbonyl group, etc. Now we do this in purely combinatorial fashion. We take, path of length 10, labeled path of length 10, carbon, single bond, carbon, double bond, carbon, nitrogen, etc. Right? All possible path of length 10, labeled both on the nodes and on the edges, and use that as a basis. It's a large basis. It has 1 million, so you get a vector of length 1 million if you do that. Very sparse. But you can work with that. Of course, training a deep network with inputs that are sparse of length 1 million wouldn't work very well unless you have tremendous amounts of data, which we don't, so you need other tricks. But I'll show you what you can do with this representation. And again, you can use the other ones. Many people have worked on this and using different techniques, but suppose you want to apply neural networks to this, well, it's going to be recurrent neural networks. And here, the interesting thing is this graph is not directed, right? So you cannot apply directly the techniques I showed you. So what are you going to do? One way would be to choose some arbitrary orientation that makes this graph acyclic. You can do that, but it's not very elegant. A more elegant solution that we developed is to take all possible orientations. So here's a molecule. It's a different molecule, but it doesn't matter. In each one of these, I have a node in gray, which I call the sink, and I orient all the edges toward the sink, right? It's not combinatorially too much because these are small molecules in organic chemistry, so they have less than, let's say, 30 atoms. And the edges are very sparse because of the rules of chemistry, right? So it's no problem to take all possible orientations in this case. And then imagine that you have little neural networks that are crawling these molecules in all possible directions. It's the same neural network, of course, you share across all these graphs. You collect the results here. If you want, you pass them through a final neural network, and you predict. In this case, it was applied to solubility prediction. And it works very well, leads to state-of-the-art results. So again, the techniques are in place. The main problem there is getting the data sets. That's the challenges in chemistry. And in some areas, you will find data for training systems. Now let me switch to the problem of predicting chemical reactions, which is even more interesting in my opinion. So you have chemical reactions, as you know, are written like this, again, strings in symbolic representations. And what you would like is, for instance, given the left-hand side, predict the right-hand side, right? Now, there's different ideas for tackling these problems. You can try quantum mechanics, and it works to some extent, but it's very slow. It's definitely not high throughput. It's not scalable, so it's a big challenge. But for certain reactions and with given enough computing power, you can do predictions based on QM. You can try to write a system of rules. If you've seen the organic chemistry textbooks, they are very thick. So basically, you're trying to compress those very thick books by writing sets of rules. Or you can try to do machine learning. So let me show you approach 2 and 3. We're now trying to combine 1 with 3. But first approach, try to write the rules. So there is a language, which is essentially the one I showed you. It's smile strings. This is the left-hand side are the reactants. This is the product. And this is just to show you that when you add them together, this is what you're getting. So it's called smirks. It's just a superset of smiles. Student of mine, Jonathan Chen, together we wrote a system that has about 1,800 rules by hand. It's very tedious. It covers undergraduate organic chemistry curriculum. And it's reasonably good for undergraduate chemistry. It doesn't do graduate level or even human expert chemistry. But it's enough to build a system that can be used for teaching organic chemistry at the undergraduate level. So we started a small company, and this system called Reaction Explorer, you can find it on the web, is distributed by Wiley now worldwide. The problem with writing rules is that it's very brittle. You get very complex system of rule for one class of reactions. And now if you try to expand the system, if you want to do graduate level chemistry, you add a new rule, you have to check that it doesn't break any of the previous rules. And adding rules has to be done by hand, which is also very tedious and not scalable. So what about machine learning the rules of chemistry? Well, again, how are you going to do that? You see, you have graphs. You have either you have to do something symbolic, or you have to deal with these graphs. And the key idea we came up with is that if you talk to chemists, the way they think about reactions, of course, is in terms of electron movements. A chemical reaction is just a sequence of movements of electrons from dense regions to non-dense regions in a very essential way. So this reaction here, which is the bromination of an alkene. An alkene is an organic molecule with a double bond. What happens is you add HBr to this molecule. The HBr first breaks down in H plus Br minus. So that's the first, if you want, electron movement. And then the Br minus attacks the double bond. And finally, you get this brominated molecule. So basically, what you have to do is you take your molecules, your reactants, and you find regions that are dense in electrons and regions that are sparse in electrons. And there is many of such potential sources and sinks. So if I give you 2 molecules, you may have 10 sources, 10 sinks. That gives you 100 combinations, source-sink combinations. And then you have to rank which combination is which set of combination is more favorable, right? Well, ranking is a machine learning problem. That's what Google does. Yandex does it all the time. So we do ranking. The way we do it is using deep learning. We put a source and a sink here, a source and a sink here, and decide which one is more favorable, right? And so you have weight sharing between the two sides. It's called the Siamese network. And we get an output that tells us which one of these two is more favorable. And if you want, you can apply this to all possible pairs and get a ranking. And then you take your top 5 potential reactions, potential electron movements, and you do it again, because, of course, a reaction has several steps. And so to make a long story short, by doing this technique, we have built now a system called Reaction Predictor, which is roughly at the level of a graduate student. And if we had more data, it's just a question of how do you get more data, we could train this and hopefully go a level above that, and maybe one day to be superhuman at predicting chemical reactions. Finally, let me shift to the third problem, which from an architecture point of view is perhaps the most interesting, which is the prediction of protein structures in biology. So protein structures prediction of protein structure is a fundamental problem in biology. The structure determines which other molecule a protein may interact with, whether it's DNA, RNA, small molecules, etc., or other proteins. Proteins essentially are sequences of length. Typical protein chains may have a length of, say, 500 letters. The letters are the amino acids. There is 20 natural amino acids. And so these sequences fold up in complex 3-dimensional structures that look something like this. And if you look at many structures, which you can get experimentally from X-ray crystallography or NMR, you start recognizing structural motifs in these structures, which are things like alpha helices. So these things are called alpha helices. That's where the protein coils on itself. And there is another type of motif called the beta sheet, where you have strands like this that are running in parallel or anti-parallel fashion, and you have hydrogen bonds between the strands. Those are called beta sheets. And then all the rest, the stuff in between, are called coils, right? So a first level of prediction of protein structure could be the prediction of where are the alpha helices, the strands, and the coil along what is called the primary sequence. Then after that, you want to produce a prediction of for instance, of the 3D structure of the protein, which is the XYZ coordinates of all the atoms on the backbone of the protein, or even better, on the entire protein, including the side chains of the amino acids. You can even move to higher levels called quaternary structure, where you have proteins that are combining together. These are two different chains that are forming a beta sheet across the two different chains by hydrogen bonds between this strand and this strand, right? So this is called the protein complex, and you can try to predict also quaternary structure if you really want to solve the problem completely. So let me describe the pipeline that we have for predicting the 3D structure of a single protein sequence. And you see immediately that you have a fundamental group problem, because the structure of a protein is invariant under translation and rotation, right? You move the protein around, you turn it, same structure, XYZ coordinates change completely. So if you put a neural network of any kind that takes the sequence as an input and produces XYZ coordinates, that is a very, very big problem. You have to deal with it up front. So the way we deal with this group invariance problem is by breaking up the pipeline into three main stages, where we start from the sequence, then we predict a number of features, including what I described to you as the secondary structure prediction. Where are the alpha helix, the strands, and the coils? You can predict other features. For instance, another very important one is the solvent accessibility, whether a given amino acid is on the surface of the protein in contact with water typically, or whether it is buried inside the core of the protein. They tend to be hydrophobic, etc. So that's another feature, very important. Binary feature, are you on the surface or not, etc. So that's this first layer of predictions. And then that's the key middle layer that deals with the translation rotation invariance. So the way we do it, we choose a representation of the protein that doesn't depend on translation and rotation. There are two ways, at least that I know of, to do that. The one we choose is the contact map. So the contact map is this binary, symmetric, very sparse matrix where you put the protein on the x and the y axis, and you put a 1 here if and only if this amino acid is close to this amino acid. So if I and j are close in space, you put a 1, otherwise you put a 0. What does it mean they are close? Well, you can use different definition. For instance, the 2 carbon alphas of the 2 amino acids are within 8 angstrom. That's a typical definition. But you can play the game, yes?
Yeah. So when you put the neural network to do all this 3D structure, the supervision signal comes from every single intermediate step? Or does it
I'll come to that. I'm not there yet. I'm just describing what's going on in each stage. So that's the contact map prediction. And you can also use contact map at the level of secondary structures. So you can take your alpha helices, take their center of gravity, and decide whether they are close or not, or alpha helices and strand, etc. So you get this other very coarse but very interesting representation of a protein, if you want, where the circle are helices, the triangles are the strands, and basically you are saying which helix is close, which other strand, etc., etc. So this is a cartoonish representation of the entire topology, but it's very useful to try to predict this coarse contact map versus the amino acid level contact map, if you want. And then from these contact maps, you want to get the 3D structure, which is, again, XYZ coordinates of all the atoms on the backbone and possibly also on the side chains. So we don't use a neural network for all these. We are using different neural networks at different stages to do different things. So the first piece of good news is that the third problem is solved. So if you give me good contact maps, let's say perfect contact map, it's relatively easy to derive XYZ coordinates up to mirror images, right? The contact map of a protein and its mirror are no different, so you cannot differentiate with that. But except for that, and it's a small detail, you can retrieve XYZ coordinates for the entire protein. This is nothing to do with machine learning. It's a distant geometry optimization problem, and it's well known that it can be solved. You can play the game of adding noise to the contact map and see, how far you can go, etc. I have no time to go into those details. But third step, consider it solved. What about the first step, predicting secondary structure and so forth? Let me just give you a sense. So here's the technique we use, again, using recurrent neural network. You have your sequence of amino acids here. It's not really a temporal sequence, so you can use if you write it as a Bayesian network, you could have an input-output HMM. So these are the input, your hidden state, and this is the output of the HMM. Because it's not really a temporal sequence, we can also run a backward chain in the opposite direction if we want, and have the output dependent on both the states in the forward chain and the backward chain. Again, this graph is completely acyclic. It's a DAG. So I like to replace this with exactly 3 neural networks, one that takes care of forward propagation, backward propagation, and outputs. So you get these 3 neural networks, recursive, etc. And this is the performance over the past 30 or 40 years. It started at 60% with Chu and Fasman, etc., progressed. When we introduced these recurrent networks in the 90s, we got it up to 78%. And the latest result we've published, we're now 95% correct. And I consider this pretty much solved because you cannot go to 100% for many reasons that I have no time to go to. The big problem is here now, how do you predict contact map? And that's the problem, the fundamental problem that is currently not solved. We have addressed it with a number of techniques. You can do the same trick in 2 dimensions where you have an input plane, 4 hidden lattices, 1 output plane. You orient all the edges in the hidden lattices towards one of the 4 cardinal corners. So you get essentially, when you reparameterize it, 5 neural networks, recursive neural networks, where the output depends on the input and the 4 hidden nodes below it. And then you have the propagation in the 4 hidden planes that is described here. Another thing you can do is to think of a protein as an object that folds in time. So you can try to predict the contact map after 1 step of folding, 2 steps of folding, etc. So you can use stacks of feedforward neural networks now that are trained using as a target the contact map at each time step, because we don't have movie of proteins as they fold for all possible proteins. Anyway, using this type of architectures at one of the recent CASP experiments, which is the main experiment, it's the ImageNet of protein structure prediction, if you want. The top 2 entries for contact map predictions were deep learning. The best is my former students, and the second best is my current students, which shows that professors have no influence on their students, basically. So in conclusion, deep learning is important, but it's not at all a new idea. I've given an example of application of deep learning in physics, chemistry, and biology. Natural science offers many other challenges and opportunity. I have not even scratched the surface here. There is tons of other problems, for instance, distinguishing stars from quasar. In cosmology, it's a very interesting problem. And not only these problems are beautiful and scientifically important, but I think they are very challenging, and they have pushed us over the year to develop more interesting architectures, in particular recurrent architectures for these problems. Thank you.
Thank you very much.